one more. Okay. Can you put?
I can see it.
It's over there. So welcome everybody. It's a great pleasure to be here, and I'm very excited to tell more about my research in robotics and also how it relates to you. So let's also welcome our flying robot, Charlie. So he will entertain us during my talk, and flying robots are one of the means for me to test my research in robotics. So what I'm going to talk to you today about is a revolution in robotics that we are currently seeing. And I'll switch to my laptop now. A revolution in robotics that we are seeing that will have an effect on how you spend your daily lives, I believe. So a large motivation for my research is a trend that we are currently seeing from robots that have been in the past usually being operated in confined industrial spaces. Like a large part of those robots have been used in the industrial environments for manufacturing, and here in the left picture you see several robots' arms that are used to assemble a car. The shift that we are currently seeing is a major one where robots become increasingly mobile, capable, and affordable. And that's a very powerful combination. And I just put up a couple of examples of use cases that are envisioned for this new generation of robots. So at the top you see robotic prosthesis where a person can suddenly grip again an object very finely controlled. Then an example below that you may have heard of in the media, delivery drones that will actually share the airspace with regular aircrafts. And two other examples are autonomous cars and shared manufacturing of robots and humans, where robots and humans can complement each other with their skills. So all these examples have something in common. It's mobile robots that share the space with us and, operate in our environment. One of my famous popular examples is the vacuum cleaning robot, who was really the first mobile robot in the home. And here you see my iRobot at home operating and vacuum cleaning the floor. So the iRobot vacuum cleaning robot was introduced 2002 and has been sold as of February 2014, 10 million units.
Excuse me, is it possible to reduce that humming sound? It's hard to concentrate
yeah.
on you.
Yeah, thanks for the comment. So, yeah, one of my a popular example is this vacuum robot, which was the first robot that really lived in our home. What these robots have all in common is they are built on amazing technology that has become available in the last 10 to 15 years. A major one is advanced sensing. So these robots benefit heavily from the sensors that you have in the phone that have become increasingly small and cheap. A phone has basically all the sensors that we need for a robot to sense its environment, including cameras, gyroscopes, accelerometers, to measure the movement of the phone, but also GPS sensor. So the next generation of robots benefit from multiple sensors that have become available, that have gotten much, much cheaper in the last 10 years, and that allow them to sense their environment, which is something their early counterparts in the industrial context were not able to do. Then on top of that, we have very powerful computing that allows them to intelligently interpret the information that they get from the sensors. And then new, smaller actuation devices enable them to interact with the environment. So because they have this sensing of the environment, intelligently interpreting this data and interacting with that, that allows them to gain a huge bunch of new capabilities that enable new applications everywhere where robots work alongside humans. And that's, a powerful area that is just being explored right now. And it's driven by these technology advances, but it is also, driven by the demand. And what we see here is the development of the market size in robotics. Robotics, if you don't know, is currently the fastest growing industry in the world. It has doubled its size in the last 5 years, and it's expected to, again, triple its size in the next 10. One important thing to see is that the yellow and the red bar, it's the home robotics and medical robotics, what we call the service and personal robotics, the robots that actually share the space with us, interact with us, collaborate with us. They soon surpass the number of industrial robots. While today most of the robots are deployed in an industrial setting, in the future the robots will heavily dominate the market, who are your personal robot. And just to quote one of my famous colleagues in robotics, who was saying if he retires, which is in 10 years, he wants to have 5 robots at his home that allow him to stay at home and live independently at home without needing the support of people, and keeps him more independent for a longer time. So we see this trend towards service and personal robotics based on the technology advancements that we had in the past 10 years. So my question for you is, will the next robot be for you? Or where can you imagine a robot helping you? The challenge that comes with this drive, this movement towards personal and service robotics is visualized here. So at the top, you see a typical industrial robot. It's highly accurate, extremely fast. We can almost, it's hard to keep track with your eyes. To guarantee safety for the environment and for the robot, it's protected with a kind of inside of a glass cage. In a real industrial environment, it looks very similar. Those robots are, in their own rooms or behind cages, so there's no danger for the human. And those industrial robots, they don't have a lot of sensing, so they just do their task in a repetitive manner. If any human would put their hand there, they wouldn't recognize and just continue moving the arm, which is a very dangerous situation. So if we now consider this trend of robots moving into our homes, there's a great challenge in terms of safety, but at the same time keeping the performance up. We don't want a robot that takes 4 hours to fold our laundry. So the challenge that really comes from the fact that those robots now operate in very complex environments that are partially unknown to the people who develop the robots. And those environments may change. I mean, you may change the arrangement in your home, you may change your habits. So it's a completely different environment that robots have to work in. They have to share the space with humans and potentially even interact with humans. So they have to adapt to the mood of the person on a certain day, and to potential changes in the environment of the human. So this gives us a lot of big challenges in terms of developing those robots, because as developers of the robots, which I'm focusing on, we have to make sure that the robot operates safely and still efficiently in situations that they don't know ahead of time. So safety and excellence in unknown conditions is the biggest challenge. And the solution approach for that has traditionally been that we have dynamics information, so a physics model of the robot, which we call prior information. So prior information is anything we know about the robot and its environment ahead of time, how the robot moves, how it interacts with its environment, how the environment looks like a map of the room the robot operates in, even what type of task the robot should exactly do. This is all prior information that we collect, but that's not enough to operate the robot safely in controlled environments. We still need feedback, which we call feedback control, where simple sensors on the robot give us feedback about the current situation and may potentially do some corrective motions. So that's the traditional approach to controls, which enables a robot to do tasks autonomously. However, as we'll see in my talk, what is necessary for this new generation of robots is really that they are able to learn on their own, on the spot, during operation. And you can imagine that if we have robots operating in changing, unpredictable environments, we as developers cannot provide them all the prior information about the environment that they would need to operate safely. So instead, what we are focusing on is that the robot can collect its own information during operation and improve its performance over time while never jeopardizing safety. So what I'm going to do in my talk now, I'm starting with the two kind of traditional areas to give you an indication of what has been done traditionally, and then I show you some of our latest research in the field of robot learning, machine learning, that enables this new robot application in the home and in changing and unknown environments. So how does it traditionally work? What is feedback control? For that, I go back to the robot that you saw at the beginning. It's a so-called quadrocopter. It has 4 motors that drive 4 propellers, and that allows us to achieve very agile and fast motions with these vehicles. They can keep themselves hovering in the air autonomously by relying on additional sensors. And the specific robot you see here in the picture and the one that we were flying has a camera as well as sensors for measuring turn rates and accelerations. So with those sensors, the robot can keep itself safe in the air. And what does that really mean? You can imagine it's similar to balancing on a rope. It's a very challenging task. If you wouldn't constantly correct and balance yourself on the rope, you would fall. And the same happens for the robot. So it's what we call an unstable system. A robot and the automatic feedback control has to constantly correct the motion of the robot to keep it in the air. And for you, it's very difficult to see because it looks perfect and easy, but it's really a constant stabilization task that is done based on our prior information and feedback of the sensors. So one way to understand it is to look at how people fly these vehicles. So if I fly this vehicle manually, what would happen is I would watch it to see what it's currently doing. That's the sensing with my eyes. Then based on my experience, usually if you fly this for the first time, you probably crash it, so you need some experience in practice. But through my experience, I kind of can compute the right actions that I have to take on a manual control to keep this vehicle constantly in the air. And that's kind of a feedback control loop where a human is doing the feedback. The human, I as an operator, keep this vehicle stable in the air. And for doing so, I need a lot of understanding of the dynamics of those systems. So we'll kind of demonstrate this for a little drone. So to give you an indication how small these vehicles can be built by now, that's one of the latest drones. It's incredibly small, and it just costs $40 on Amazon. So this technology has really become, a commodity. So we demonstrate you manual control where Chris is flying it manually. And Chris has practiced a little bit, so he's pretty good at it. But what I'm gonna do to show you how difficult it is to keep it stable in the air, I will just blow at the vehicle. And Chris is still trying to keep it in the air and stabilize it. Are you ready? Yeah. Okay. Maybe a bit, a bit further down this way. Just, is it fine? Yeah. Okay. So you see, his goal is to keep it stable at one point in the air. And if I just blow a little bit, the vehicle is heavily influenced, and it's very hard for him to stabilize it at one location. Okay, again. Now you're better? Okay, one more time. Okay, so it can be really hard to stabilize it at one location based on disturbances. Okay, thanks. So what we do when we talk about feedback control or automated control, it's exactly the same loop, but the human is replaced by a computer. So we have sensing, this time sensing on the vehicle, a camera and motion sensors. And those sensors report their information to a computer, and the computer then computes the correct actions to keep the vehicle stable in the air. Ready? And so we are demonstrating it again with this vehicle. And what I'm going to do is the same thing. I will disturb it, but because it's a bit bigger, instead of blowing, I just push it. And you'll see how the computer tries to elegantly bring it back to its original location. Ready? So now it's fully autonomous. So Chris is not doing anything anymore. It's just flying based on its own sensor measurements. And if I now push it, it nicely comes back to its original location. So I can push it in any way I want, from any direction. And it, nicely, gracefully comes back to its original position. Okay, one more. So what we see here is, thanks. What we see here is that the computer is incredibly good at doing this, and what it needs, what it requires to do its job is it needs a mathematical model, a physics model about the behavior of the system. So all this computer control relies on physics. So we need to first understand how the system works, and then we can implement the correct rules for it to stabilize itself at a certain location. The mathematics are really important. That's often the most tricky part, to describe the behavior correctly by equations. Once we have that, we can then use controls rules to compute the next, the input. And in this case, it's done 800 times per second. So there you see already the big difference to how humans operate. The sensing is very, very precise. If we, as a human, look at this vehicle, we don't have a good sense of 3D position. So the sensors that are on the vehicle are much better in detecting its own position and deviations from the position. Then the computing is much faster. So once deviation from the original position was detected, the computer can react very quickly. So in this case, it computes 800 to 1,000 times per second a new update, while a human has already just a reaction time from 30 milliseconds. And then the actions can be very precise. You know, the computer control is not limited by our manual control abilities. It can output numbers with high precision. So ultimately, this computer control allows very precise, repeatable, and reliable operation. And that is, we use it here to hover the vehicle in the air, but computer control is used in a variety of devices that you will all have at home. One of the most popular ones are air conditioning systems, where you have a sensing device and an action. You sense the desired, or you sense the temperature in the room, you have set a desired temperature, and there is a way to cool or heat the room to react on deviations from your desired temperature. So controls is not limited to robotics per se. So this is a very powerful combination already and allows robots to do tasks on their own, here in this case to stabilize itself in the air. But computer control can do much, much more than that. It enables behavior that would not be possible otherwise. And one example where we show this in the lab is when we fly multiple vehicles in a coordinated way. So I have a couple of videos on that just to show you the power of controls. So here you see multiple vehicles flying from one configuration to another that we had pre-programmed, and their flight path is completely computed automatically. So they find a flight path that is the fastest while still avoiding collisions. And that's all done in real time and autonomously. So the only thing we did was we generated these configurations at the beginning, and the vehicles fly from one configuration to another. So you can imagine that's impossible to do with humans. Even if you have 5 expert pilots, coordinating their manual control is incredibly difficult. Another example where this is even more obvious is we fly them to music in a coordinated fashion. And this is one example. So that nicely summarizes, thanks. So this nicely summarizes the power of the traditional feedback controls. However, there is a challenge and limitations to this approach. And I'll show you 2 examples. The main intuitive way to understand this is, as I explained you before, those controls algorithms, they rely on mathematical equations that describe their behavior. And to know these mathematical equations, we need to know the robots and their environment very well. And what I've showed you, even the flight, here and in the lab, that was still a very controlled environment where we know the space is empty and there are no wind and no large temperature changes and so on. So I want to show you 2 examples where this can easily fail. One is when we fly these vehicles very quickly, and I show you a slalom flight where the vehicle should fly around those poles as quickly as possible. At that point, we have aerodynamic effects that we don't fully understand. There are some qualitative measures of them, but no quantitative models that we could use in our controls. And then we don't have a basis to fully understand how to control these vehicles. The second example is when we have a ground vehicle and we want to do fast path following again. As there are a lot of difficult interactions between the soil and the vehicle itself that are very difficult to understand, we also see that traditional feedback control fails. So I'll start you with showing you the first video where we try to do a slalom motion at high speeds just based on our traditional controls. So you see, it didn't look like a slalom, it crashed. So it already hit the first pole, just because our models are not accurate enough to do this task. The second example is a ground vehicle. It should follow its own tracks at a higher speed, and it gets off the track because in this turn at high speeds, we don't fully understand the behavior of the robot and its interaction with the environment. So in both cases, the traditional controls approach fails, and these are still lab examples. You know, we are not in your home or in a real environment. Why is that the case? Yeah, there are some dynamics that we don't understand and that are not part of our model. And the other reason are external disturbances from the environment. You can imagine if a robot drives on snow or at a side slope, and we don't know this ahead of time, our models will not accurately represent its behavior. And the same for the flying vehicle that I showed you at high speeds. So model inaccuracies limit the achievable performance that we can obtain with traditional controls method, but they also jeopardize safety. You saw the ground vehicle get off the road. I mean, if that would be your autonomous car, that would be extremely dangerous. And the same for flying vehicles. So to address this problem and to bridge the gap towards robotics applications in our real environments, we look at combining controls with machine learning, where machine learning allows the robot to gather information during operation. And the first example I want to show you or explain to you is how we do learning. You can imagine it's very similar to how we humans learn. So if you throw a basketball, the first time you likely will not hit the basket. But through practice and through observing your performance, you can learn and improve over time. And the same holds for basically any task we do. If it's playing a music instrument, driving the car, we get better every time we do it by learning from our mistakes and improving on ourselves. In the same way, we enable robots to learn. The key requirement that we have is that a robot can judge its own performance. If that is not possible, then it's hard to get any feedback. But if the robot, after executing a task, can judge its own performance, we can use this information to improve the behavior the next time around. And very similar to a human, it's kind of a gradual improvement. So the more often we do it, the better we get. And so for the slalom learning that I showed, or slalom racing I showed you before, I show you now a video where the robot actually practices above the poles until it knows for sure that it can make it around the poles, and then it dives down and does the motion. So here you see it starting learning, and we practice above the pole because during the learning, we cannot make sure that it actually goes around the poles with the method we use here. So it doesn't take many iterations for the approach we use here to converge and learn. So this is iteration 2. It learns on the forward and the backward path. That's the third time it is trying it. And after the third time, it's certain, and it goes down and actually performs this motion. And from the data, we also know that it wouldn't be able to do it beforehand. So that was the first time it could have done it. And here you just see different other configurations, but I have to say, this is after learning. So for every new configuration for this type of learning we use here, it needs to practice again. And here you see the motion that it did before, where it failed before the video I showed you before. So through learning and repetitive practicing, we can enable robots to learn a very specific task. However, one big aspect that you saw in the video was it was learning above the poles. So we couldn't guarantee safety of the actual task during the learning phase. So during the learning phase in the first approach I showed you, we couldn't guarantee that the vehicle would not hit the poles. So a next step that we took in the research was that we were asking how can we achieve high performance eventually, but guarantee safety during the learning process at all times. And that's incredibly important if you think about the real world applications. You would never want the robot to fail, at least for most of the tasks. There may be tasks where failing is an option, but generally we want to just improve the performance while never jeopardizing safety. So what we did for this new approach is we combined again a traditional controls method with an online learning method, where the traditional controls was good at guaranteeing stability and modeling necessary uncertainty in the system, and machine learning in its general form is very good at improving the performance of the robot over time. So what we did is we combined those two techniques to enable a robot to improve online while still guaranteeing stability and safety during the learning process. And I'll show you two videos that these are very first demonstration of the concept. We haven't yet deployed it to advanced applications. But it gives you an idea. But one is about driving again, and to understand the driving example, you can just think about yourself when you drive. If you have an autonomous car, it doesn't know ahead of time what the conditions on the road are. And it's impossible for us as developers to tell the car in some form or another, so it has to figure it out on its own. However, what we don't want, which would be one way to solve this problem, we don't want our car to drive as careful as it drives in winter all year long, right? That would probably kind of annoying, and you would never use the autonomous mode. So what the idea is we have this safe controller that allows the robot to drive safely under any possible condition, snow, summer, a lot of rain. But after a couple of seconds driving with this safe controller, we gain enough information such that we can conclude what situation we are in and improve the performance over time. So looking at our sense, decide, and act kind of loop from before, what happens is, in addition to the physics equations that we have from our prior information, we use experience to make decisions and to operate the system. So in the car example, what it would do is it would start driving slowly but safely, but as it gains more information about the environment and the current condition and the road conditions, it would speed up over time. because it's more certain about the condition. So one example is the example I showed you before, where we first we teach the robot what route it should go at. Then if we immediately go at 1 meter per second, we saw this before, it would fail. But now we slowly, the speed is slowly increased, and while driving slowly, the robot is gaining more information about the path, about its environment, about the interaction with the environment. So we slowly increase the speed. And if we slowly practice with increasing speeds, it can now do, this last trial was at the speed where it failed before. So here you see the full run at the speed where it failed before. And this is just, still a lab environment at our Institute for Aerospace Studies, but it shows the concept that a robot can guarantee safety by starting slowly, learning about the environment, and then increasing the speed over time. Another example I show you is where we tested it on the flying vehicle, and this time we really wanted to challenge this learning system, and we basically didn't give it a priori information at all. So we just said, okay, start almost from scratch. So we didn't do much modeling, we just gave a very simple model. And then we allowed it to learn. And you can imagine for the driving robot, the robot can get off the road, but for a flying robot, it's much more challenging because if the robot would just do one single mistake, it would fail and crash. Right? So for flying vehicles, it's like a necessity that we guarantee safety during learning. So I'll show you the approach here. So we start with basically almost zero knowledge. That's what you see at the top. And then at the lower picture you see, it was collecting data for not more than 40 seconds. And the performance is much, much better. Here you see the initial controller again. It's very conservative, very slow, very careful, and then this final controller quickly gets it back to its desired position after disturbance, while never jeopardizing that the vehicle crashes during operation. So that kind of shows you some first steps that allowed us to kind of connect between what traditional controls could do and what was sufficient for today's robots that are in a confined space, in very predictable, encounter only very predictable situations. And the new robots that we want to deploy that operate in our space together with us, drive together with us on the road, and work in our homes. So we kind of did a first step, but there are many open questions, and there's a lot of work still to do. I just highlight a couple of them. We do show that we can guarantee safety in the examples I showed you, but it's still a challenge to envision whatever could happen to the robot and make sure that we guarantee safety at all times. Another one is we haven't looked into how we can achieve effective human-robot interaction, where humans are all different. We would require the robot to adapt to the human in a very safe and reliable way, for example, for robotic prostheses. So there are lots of open questions, but we showed some first proof of concept examples that demonstrate that past experiment data can be useful for robots. They can interpret this correctly to improve their performance over time, and we showed some first approaches that address the safety concern during learning. So this should all lead to robotics applications, and I just want to highlight a couple that we have been working on or are working on and where the challenges are. So one is drone delivery, or any operation where the payload, what we call, on the drone changes. So this is an operation where we would like to use safe learning, because let's say if we have a delivery drone, we don't know the mass of the package necessarily beforehand. And if we would even know the mass of the package, we don't know its inertia properties, which heavily affect the motion of the robot. So ideally for delivery drones, or any drone that carries heavy sensors, we would just want the robot to learn this additional payload on its own and adapt its behavior, which would mean in practice intuitively that for a large and heavy payload, the robot would rather be acting slowly, while with a light payload, it could fly quite aggressively. Another application that we have been looking at is a collaboration with the MIT Sensibility Lab, where we use these drones for environmental monitoring purposes, where we actually fly multiple drones. And here, the drones could actually learn from each other and improve their flight performance over time. The challenge here is that they carry different sensors, different mass that affect the dynamics, but they are also affected by wind and temperature changes and should land on the water, and the kind of behavior of the landing over water is something very difficult to model, which we could learn over time. But this shows you also some potential of these flying vehicles in real good applications. So in this case, we were monitoring toxic algae in lakes. And those toxic algae, if they plume and die, they can make drinking water toxic, which happened last year or a year before at Lake Erie, where people couldn't use their drinking water for a long time. So if we had reliable flying systems that can go out every day during any weather condition, monitor the situation of the algae, we could avoid algae bloom eventually and avoid situations where drinking water becomes toxic. So there are lots of applications. These are just a couple of them that we have been working on that really require safe learning techniques to be useful in a reliable and safe way on a long-term basis. So to sum up, there is a big shift in robotics, and it's really exciting, and I'm sure it will affect any one of you, I hope in a positive way, where we see robots entering our world and operating and collaborating with us. And robot learning will be an essential technology for this next generation of personal and service robots. So to finish, I finished with a quote for you to think about in the next little while. So this technology has been thought of an extension of the human body by many people before. So it is our responsibility, but also our opportunity to use this new technology to, enable things that we couldn't do alone. So think about which robot will be the one that you can benefit from. And what I've showed you today is, collaborative work with lots of people, both at ETH Zurich in Switzerland, where I did my research before and where I still co-supervise a PhD student, as well as at the University of Toronto, where I in particular collaborated with Professor Tim Barfoot on the ground vehicle work. And a very special thank you goes to the people here who are kind of both PhD students of mine and operated the drones today. And to kind of finish the show, we'll show you one interactive demonstration where we show the vehicle a little tag, and it interacts with the human, and the human, by moving the tag, it can move the robot and move it from the stage, and that will conclude the talk. Okay, let's see. So Karime has this talk on the phone, and by just moving it around, she can interact with the robot and move it. So she's just pushing it from the stage. So what the robot does here is it keeps a fixed distance from the drone, and if she moves down, it moves down, and if she moves forward, it moves forward. Thanks.